And so I will talk about injection pressure and temperature effects on fault integrity. So you will, in the coming half hour, you will hear me talk a lot about pore pressure changes, temperature changes, and how that affects stresses and how that affects faults and fractures. So fault integrity in this sense, you could maybe replace it with fault reactivation, right? So we're going to look at how stresses on faults and fractures change if you are active in the subsurface and if you are active in geothermal. Okay, so first of all, I'm going to be maybe a bit boring for some people when I talk about total and effective stresses on faults and fractures. But I think I have to introduce a few basic concepts in order to understand the rest of the talk. I'm going to go into a bit of theory of uniaxial pore-elastic stress changes and how that affects fault stability when you extract fluids, and then I will step towards what that means when you inject fluids, and I will talk a lot about stress path factors in this context. Then I will show that, okay, analytical solutions can go a certain way, but you know, real situations are more complex. For instance, with a tilted SV or S1 rather, you know, non-horizontal, non-vertical principal stresses, or very specific fault geometries which go beyond what you can do with analytical methods. Different stress regimes, you know, normal fault, strike slip stress regimes, all play a role. Then I go to thermoelastic stress changes, and I will present in between, not only in the end, I will in between present sometime a case study result. So bear with me if you already know some concepts, but I hope that a lot of people will actually have an effect of, oh, now I finally know what's behind all this, right? So let's start. So this is an example, nothing geothermal here. This is just a conventional results or situation in a conventional oil gas reservoir, a stacked reservoir in Malaysia, in Sabah, in the Borneo shelf area. So gas and oil have been produced from this reservoir. So there is an initial reservoir pressure of almost 4,000 psi. Then production has happened. Of course, the pore pressure reduces, the reservoir pressure reduces. So we move to the left. And after production has happened, actually nothing happened in the field. So slowly, because of aquifer influx and repressurization, there is a recovery phase where the pore pressure goes up again. Now, so that's nice for the x-axis. Now, what do we see on the y-axis? There is a change, like this estimated maximum effective tangential stress increases as the pore pressure goes down, and it decreases as the pore pressure goes up again. So what this means is that my stresses acting, in this case on a horizontal perforation, will obviously change when the pore pressure changes, and when the pore pressure goes down, effective stresses go up, and when the pore pressure goes up, then effective stresses goes down. And so you can see that relationship here in this graph. Now, when you then start to inject water, and in this case it was for an enhanced oil recovery, you see actually a model result for 3 different injection temperatures. And so if you have your cooler water injection temperature, injection water temperature, you get a stress change. Yeah, the cooler water reduces the stress on the perforation, and the cooler it is, the larger is the stress change. And if you continue injecting, you increase your reservoir pressure, and so the effective stresses go down. Now, maybe you didn't get all of that. But basically the message is, if you change the pore pressure, stresses will change. And if you change temperature, stresses will also change. And obviously that affects something in the subsurface. So let's start really simple. How do we model stresses analytically in the subsurface? Basically, we start off with a very simple case. We say most of the time that our vertical stress is a principal stress, and therefore there are two horizontal principal stresses. Sigma 1 is the largest, sigma 3 is the smallest, and sigma 2 is the intermediate principal stress. And in the way they relate to each other, you can then have a normal fault regime, a strike slip fault regime, or a thrust fault regime. Now, as mentioned before in the first talk, most of the time we are dealing with a normal or a strike slip fault or stress regime, and more seldom with a thrust fault regime. Okay, what's the difference? The difference is that in the normal fault regime, the vertical stress is the largest, and the two horizontal stress are smaller than the vertical stress. In a strike slip fault or stress regime, one of the horizontal stresses, the maximum horizontal stress, becomes the largest stress, and the vertical stress is intermediate, and the third principal stress, which is the minimum horizontal stress, is the smallest. Okay, so we start off with three principal stresses. Later I will come to the point that these are not always, principal stresses are not always vertical and horizontal, but we will start with this case. Now we connect pore pressure to that principal stress, which is a total stress. So the principal stress we saw before is this yellow sigma here. It's a total stress, and it acts on both the grains in the rock, and it's counteracted by the pore pressure in the pore space in the rock. So the net result, what we call the effective stress, sigma prime, that is the let's say the real stress acting from grain to grain, and that is the stress which causes deformations, which causes failure, which causes movement in the earth. So if we now subtract the pore pressure from the total stress, we get the effective stress, right? That's very simple, very easy. But notice that there is an alpha here, which is the biofactor. It's a rock property. You can calculate it by 1 minus the bulk molars of the entire rock divided by the bulk molars of the individual quartz or feldspar or clay minerals in here. So typically, or theoretically, the biofactor can range from 0 to 1, theoretically, but practically it is more around the higher side of the scale, so around 0.7 for stiff rocks. It can be lower, it can be, so I've seen cases of 0.4, so it can be that low, but if you get a softer rock, it will approach a value of 1. Now, why do I go so much into this theory? Because later we'll see a slide where the biofactor actually quite influences the state of stress on a fault and can actually determine whether that fault reactivates or not. So it's often an undervalued factor, and often we say, we don't know the biofactor and we assume it's 1. But is that really the thing to say? So we will look at that later. So once we got the effective stresses, you can see here a fault plane, and that fault plane has a certain azimuth and a certain, a dip direction and a dip angle. The dip angle is beta. There is an angle lambda here, which tells you what is the relationship between the strike of the fault and the maximum horizontal stress direction. So you see 3 effective stresses: a vertical, maximum horizontal, minimum horizontal effective stress. And depending on how beta and lambda are oriented, we can always convert these 3 stresses into a normal effective stress acting perpendicular on the fault plane, and a shear stress acting parallel to the fault plane, right? And it's that effective normal stress and the shear stress which determine whether the fault will move or not when you compare it to a more Coulomb failure line. which is shown over here. So here you got a more failure line. This is your effective normal stress. This is your shear stress acting on the fault. Now, and now comes a thing where we go to the reactivation of faults. So in the subsurface, you can have critically stressed faults or fractures, and according to the hypothesis by Zoback in his Professor Mark Zoback in his book Reservoir Geomechanics, he actually mentions that critically stressed faults or fractures are in general hydraulically conductive. That means they can pass fluids, they're permeable, they can leak basically. But also if a fracture or fault moves, that can lead to induced seismicity. Now, induced seismicity doesn't necessarily need to be a problem if it's sufficiently small, and it depends on the area in which you are. But if we talk about let's say a European or maybe zoom it into a Dutch context, infrastructure is not used to induce, is not built, not constructed for induced seismicity, which becomes too large. So you might want to avoid that. Yeah, so faults can be critically stressed naturally, simply by the in situ stresses. So they can be at sharp, so to say, by the natural stresses, or they can be put at sharp by human intervention. This picture down here shows you why a critically stressed fault is hydraulically conductive, because if a fracture or fault moves and it has a bit of an irregular surface, there can be a dilation, and that dilation, when it moves, the fault can remain open for a while. Depends on how brittle or ductile the rock is. But then in that period that it's open, it can actually leak fluids. And moreover, if we change our stresses, so we go from an initial stress state, this is a Mohr circle for the initial stress state. So here we are looking at a fault, the combination of normal effective stress and shear stress on a particular fault, that can actually move towards failure, and that's how we can reactivate a fault. So how does that work in terms of analytical solutions? Now, in order to understand that, we need to look first at our poro-elastic equations for horizontal stress. So if you take this equation, which is basically a 3D solution of Hooke's law, when you put a stress onto a sample, you deform it according to the Young's modulus. There will be a vertical and a horizontal deformation, which is given by the Passer ratio. So anyway, this is the poro-elastic equation to calculate minimum and maximum horizontal stress as a function of elastic rock properties, vertical stress, the BO factor, and pore pressure. And then there are two tectonic strains, basically how much you press from the horizontal side. Now, I don't want to go in too much detail on this equation. Where I want to go in more detail is if you deplete a reservoir, if you produce oil or gas, and I know we are talking now about transition, so I will come to the injection later on, but if you extract oil or gas, you reduce the pore pressure. When you reduce the pore pressure, effective stresses go up, and therefore the reservoir will compact. So if you look at a laterally very extensive reservoir, like a pancake structure, very thin but very extensive, the reservoir actually will compact vertically. So the vertical stress will keep on pressing onto the reservoir. So your total vertical stress doesn't change, but your total horizontal stress will reduce, because the reservoir also wants to contract laterally. Yeah, it wants from left, it wants to go to the right, and from the right it wants to go to the left, but it can't because it's held back by the side burden. So the side burden is kind of pulling on the reservoir. So when you then say, okay, my horizontal deformations, my horizontal strains are 0. So in this equation, you put epsilon 0. What will be your delta sigma h, your change in horizontal total stress? Well, that is all of this elastic properties times the change in total vertical stress minus the PO factor times the change in pore pressure plus here a pore pressure change term. Now the change in vertical total stress is 0, so that falls out. So if you solve this, you will get actually this equation here, where you can actually calculate the total horizontal stress change as a function of the pore pressure change, the BO factor, and the Poisson ratio. Yeah, so if you simplify this term with the rock properties, you can actually calculate what gamma is. Gamma is the stress path factor, or SPF. So the stress path factor is the change in total horizontal stress divided by the change in pore pressure. Yeah, so the message here is basically 3. When you deplete a reservoir, message 1, the vertical total stress doesn't change. 2, the horizontal total stress reduces. And 3, you can calculate from these analytical rock properties, the BO factor and the Poisson ratio, how much that total horizontal stress change will be for uniaxial conditions. Now, if the total stresses change, and you connect the total stresses to the effective stresses via the equation we saw before, you actually get this behavior. So my vertical effective stress will now increase by an amount of minus the BO factor times the pore pressure decrease. Okay, the horizontal effective stress will increase by this amount. So it's the pore pressure reduction, a decrease with a minus sign, so it's an increase, and then the BO factor and that stress path factor come in. So what does it mean in practice? Let's look for 2 different stress path factors. So this is my Moore circle for initial conditions, initial pore pressure. So I'm at a certain effective stress level. If I now decrease the pore pressure and I have a stress path factor of 0.5, my vertical effective stress moves from here on the right-hand side all the way to here. That's a relatively large change. It's almost the entire pore pressure change times the BO factor. Okay, the horizontal effective stress changes from here to here. The increase is much less because it's basically the BO factor minus that stress path factor. So I'm going from here to here. So if I would be on a fault, I move from this point to this point, and actually you see that you are kind of roughly parallel or moving away from this failure line. So you are okay for a stress path factor of 0.5. But if you have a stress path factor of 0.8, you actually can move towards failure. Okay, so what does that mean? We are looking here at a certain starting point. So if my fault has a certain orientation, I'm looking here at a point on this circle, a starting point. If I deplete a reservoir and I have a certain Poisson ratio, 0.4, then, and I deplete my reservoir with a certain amount, a certain pore pressure change, I can move away from failure if I have a high Poisson ratio, but I can move towards or really at failure for a lower Poisson ratio. For injection, this is exactly the other way around. If you apply the equations to injection, so you actually increase your pore pressure, your effective stresses go down. But if I have my higher Poisson ratio, I will move towards a higher shear stress, so towards failure. But if I have a lower Poisson ratio, I can actually move away from failure. Now this is where the BO factor actually comes in. You can see 3 very reasonable BO factors, 1, 0.9, 0.8. And you can see that in terms of the steepness or the incline of my stress path, not much happens like the stresses move up and down with the same angle or with the same relationship between normal effective stress and shear stress. But the starting point becomes different, right? Because my effective stress is the B factor, is the total stress minus the B factor times the pore pressure. So if the B factor is higher, I subtract more pore pressure, and so I get a lower effective stress. So my starting point changes, and that determines whether I move quicker or slower towards failure. So if you would combine, let's say, a BO factor of 1 with a Poisson ratio of 0.4, you would actually be in pretty bad shape in terms of injection. Yeah. So what is bad for injection is a high Poisson ratio and a high BO factor combined. Okay, so here I'm coming to injection soon. So here I put the effect which fluid extraction can have on fault reactivation. We are looking at the northern Netherlands here, the Groningen gas field, a giant gas field, which recently has been shut down. It has been shut down because of fluid extraction, reactivating faults, creating induced seismicity events, which maybe for New Zealand standards are not very high, but they went up to 3.4, 3.5 on Richter scale. So for Dutch standards, that is high, and many farms and houses and construction sites are not designed for such small earthquakes. And so you get serious damage, and hence the field is shut down. Now, closer to our home in Malaysia here, this is in Brunei, we can actually see how the stress path factor can be measured in the field, right? Here there are different leak-off tests done, 3 different leak-off tests in 3 different years. They give an indication of the minimum horizontal stress. And of course, we know the pore pressure at the time the leak-off test was performed. So you get these data and can then calculate a stress path factor from those data, 0.84. So that means if you don't take into account the stress path factor, your Mohr circle would move from the left side horizontally, let's say, to the right side. As you reduce the pore pressure, effective stress increases. But if you take into account that 0.84 stress path factor, you see that your Mohr circles increase because my vertical stress changes, but my horizontal stress hardly changes because my stress path factor here is so high. So we move towards failure. Now, in those early days, there was always the unclearness. If you inject, how will the stress path factor actually move? Will my Mohr circle move to the left, or will I actually reduce in size?
That's 5 minutes, Frans.
Yes, I thought so. You were warning me, so I will speed up a little bit, not to worry. So this is actually a numerical model result. We can see it's a 2D model. There is a reservoir here. This is done by late Bogdan Orlic, a former colleague and friend of mine. And so he modeled in 2016 stresses in the reservoir, and you can see the effects of the depletion, but you can also see the effects of injection. This numerical model actually predicts that you, if the geometry is simple, that you actually move back along the same stress path as before, and if you continue injecting, it remains like that. Yeah, so our Mohr circle here should actually become smaller. Okay. Earthquakes to fluid injection definitely can happen because you can definitely move towards failure, as you can see here. And for geothermal, that can be a problem, like in this case in Alsace, France, where induced seismicity was triggered, and therefore they have to investigate first how that comes and whether they can operate safely if they want to pick up the project again. This is some data by ETH Zurich, the university. So induced seismicity located to geothermal is actually a common thing. It's just a question, you don't want to have it too large to the point that actually you notice it at surface or causes trouble at surface. Okay, now of course stresses are not always vertical and horizontal. If you have salt piers or structures or fault structures, you can see here is a stiffer reservoir, and stresses actually tend to move towards that stiffer rock. Stiffer rock tends to carry more stress, so it attracts kind of the stress. So you cannot get away with simple analytical solutions anymore. Furthermore, if you deplete or inject even stress, here we see the maximum horizontal stress azimuth that can actually change during depletion. So in essence, you need actually, maybe you can start analytically with a quick look analysis on how your rock properties affect stress paths and therefore how close you're going to get to fault reactivation. But ultimately, if you want to do the job well, you need at least 2D, if not 3D numerical models, because we can see that fault geometry plays a big role. Here we are looking perpendicular to a fault plane. And if there is no throw, you can see that your fault reactivates, but there is hardly any displacement. There is hardly any movement along the fault. So you expect that any seismic event would be small resulting from this. But if you have a configuration like here where you have a throw and this part of the reservoir goes down, the bottom goes up, you get more displacement along the fault plane, more centimeters, right? You really talk about 10 centimeters of movement. So that can cause definitely induced seismicity. About the stress path factor, here we can see that a numerical model confirms the analytical solution if you are far away from the reservoir boundary, but once you come close to it, stress path factors can become smaller, and even the vertical direction can have a stress path factor which is non-zero. That means vertical stresses, total stresses can definitely change if you are stepping away from uniaxial deformation conditions. And that is illustrated here by this numerical model result. So you can see as you deplete these wide reservoir zones, vertical stresses here increase at the sides, but they decrease above the reservoir as the vertical stress tends to arch towards the side of the reservoir. And also the shear stresses on the faults can change accordingly. Now, I think I just need 2 or 3 more minutes, Gerald, so not to worry. If you change your stress regime, here is an example of normal faults in a strike slip stress regime, meaning my maximum horizontal stress is now larger than the vertical stress, and at initial stress conditions, really initial pore pressures, this fault is actually already at sharp. It's a stress level of 1, meaning it's actually critically stressed. But as you produce, this fault stabilizes. But imagine if you are in this type of situation with geothermal and you inject fluids, you would actually directly trigger movements along these faults straight away as soon as you inject. 2 more slides. This is temperature effects. So notice that I spent a lot of time on pore pressure changes. There is only 2 slides on temperature, effects of temperature changes. In essence, if you go again into uniaxial conditions, meaning no horizontal strain, you can actually calculate changes in horizontal stresses analytically. But again, you should probably do it numerically. So if you inject a colder liquid, you have a certain pore pressure change, which might be okay. So you're thinking, oh, I'm far away from failure. But don't forget about the temperature effect, because here we model or not I, but Bogdan Orlic again modeled a 50 degrees Celsius temperature reduction, and that can cause these horizontal stresses to change while the vertical stress remains unchanged, and you can definitely move towards failure. So I will skip this for now and come to my conclusion. So we saw that fluid injection and extraction, both cases, can lead to stress changes, both total stresses, but important for fault reactivation are the effective stress changes. We can actually reactivate faults, both when we extract fluids, but also when we inject fluids, and that can lead to leakage and induced seismicity. You can approach this maybe in an early project state analytically, but ultimately I think you cannot get away without looking more complex with numerical models, at least 2D models, to include more complex geometries and different rock properties in your system. But whatever you do, the final message I wanna give is that even though a situation seems severe, like there is a fault and maybe in a pilot project like in Alsace, a fault has been reactivated and caused in induced seismicity. I think there is almost always a way to adjust your operational limits, like your temperatures, your injection rates, your injection pressures, to come within, let's say, a safe zone where actually you can significantly reduce the risk of fault reactivation and therefore leakage and induce seismicity. So now I've used up already 3 minutes of my Q&A time, but that's definitely what I wanted to say.
Thank you, Frans. That was a very comprehensive review on injection pressure and temperature and how it affects fault integrity. We have one question in the question thread, again from Attila Petrick. Frans, how do you derive stress path factor and how does it influence the stress magnitudes if you have depletion or injection? You mentioned it, and it would be nice if you could elaborate on this a bit more.
Yes, so that is actually a good question. So it comes back to my the slide. I'm gonna support my answer with a slide. So the first approach is to go via these analytical equations, and you might not know at all what's your BO factor. You might not know what's your Poisson ratio, but at least you have a certain range, right, to play with. Like you know whether you have a stiff or soft rock, so you know whether your BO factor is on the higher side or on the lower side. So you can establish kind of a range of uncertainty there. The same with the Poisson ratio. So you can at least start calculating a stress path factor and put it basically in Excel, like what I did here. Get your fault orientation. Calculate your normal effective stress and shear stress on the fault, and make some back on the envelope type of quick analytical calculations. But you can add core, like rock measurements to it, or if you have a well, you maybe have acoustic measurements. You can calculate some elastic rock properties from logs. Maybe you have core measurements, and ultimately, if you want to include, let's say, complex geometries in the field, because sometimes your stress path, you have arching effects in your field, like your stress path factor can be different at the side of the field rather than in the middle of the field. So if you measure it in situ, that could help. But yeah, if you don't have any data because you just started a project, this might be a bit difficult. But maybe you can have some data from a nearby reservoir which has been producing already for a while, if that's applicable. I hope that answers that question.
I think so. I hope so. We only have a few minutes left, so the questions are in the Q&A area. So perhaps Attila, if you have any further questions, please add to those. I've assigned your question to Frans. He can answer. There is a follow-up question from Nader Fardin. Hi, Frans, as always, a great presentation. Could you please give more details on 2D numerical model where stress paths for both depletion and injection were the same?
Yes, so that is this model, right? This is a 2D plane strain model, so that means there is no deformation in perpendicular to the screen. So the deformation all happen in the 2D square you're looking at, and because of the perfect geometry here, like there is no throw on the fault. It's actually nice to see that the numerical model confirms the analytical model if the numerical model has the same assumption as the analytical model. So it's kind of a confirmation. But as soon as you get a bit of throw or complex structure in here, or a bit of a bend in the fold, and then the story becomes, I can imagine, becomes a bit different. And this also, notice that, sorry if my answers are a bit long, I know there are more questions, but there is this thing about how you see the numerical analytical model knows the pulse rates of the Young's model, but reality, the rock, first depletes and then injects. It might actually deform in a bit different way as the mechanism, the injection might go in different, the pore space has changed, and so there might be a bit of how do you call this effect, like you don't go back maybe exactly along the same path. Again, maybe I raised more questions now than I answered, but
we've got 2 questions remaining, and perhaps we can get through them quickly. First is from Sirikarn. Hi, Frans. Thanks for the nice talk. Does injection rate play any role in a change of stress state?
Injection rate, yeah, I would say yes, because your injection starts from the wellbore, and so if you inject faster, you get a higher bottom hole flowing pressure in your wellbore, and that leads to a higher pore pressure near the wellbore. And therefore also maybe lower temperatures near the wellbore. And if that continues long enough, it actually goes away from near wellbore effects to reservoir effects. So injection rate definitely can influence your pore pressure and temperature distribution throughout the field over time, and therefore also the stress changes.
Great. We've maybe just got a little bit of time for this last question. Hi, Poppy, from Poppy Edgecombe. Have you used well flow data and related seismic events to compare against the analytical calculations / assumptions for that specific project, ? If so, do these seem to line up as expected?
Well, that answer will be very short. It's no. So these are model results, but there is more to it, right? So here, let me see. We have built a model of this situation in this reservoir. So actually, the events you see here are actually modeled with this model here. I didn't connect it in my talk. But you definitely can see a correlation. Like if you have this type of fault, you have more seismic events happening than if you have this type of fault. Like you can see that actually in this picture, where you have the bigger offsets here, you got this yellow going in, right? Here you got this yellow going in. There are more seismic events there than related to your faults, which remain in that green part where your throw of the fault is less. So again, I hope I didn't generate more questions.